So a file is it's an API on Unix, and we can use file API for a lot of things besides reading and writing to files on disk. On Unix, pretty much everything is a file. So the kernel exposes lots of things as files through the file API, by which I mean you can open, read, write, close, sometimes seek, clone, send file. There's a bunch of system calls that you can call on a file descriptor. So like the files in /dev, for example, these represent devices. They're still files. I can still cat like, hello to dev, and then let's see, what TTY am I on? Oops. I'm not sure what PTY I'm on here, but here we have, let me see. So there's like dev mem, and that's a file that represents all of memory, just linear file representing memory. I can write a bunch of garbage to it and I'll probably crash my system. There's video for Linux, all these TTYs, which represent a console. So if I knew what console I was on, and I forget how to look that up.
Usually
7? Oh, don't know. PTS is like a pseudo TTY. TTY is a teletype interface, which is like a console. It's like something you can sit at and type stuff on. It used to be a printer hooked up to a keyboard, not like a fancy, monitor. So that was called a teletype. So that's why we still see TTY. Anyway, it's a file. Standard in, standard out, standard error. Those are files. See? So if I echo hello to dev standard out, I get hello. And why do I get that on my console? Because this is hooked up to standard output. So I can open, so standard output is a file. I can open it, I can close it, I can write to it. And if I do, stuff appears on the console here on my TTY because it's hooked up to it. You can even look at standard out in more detail here, and I can see that it's actually a symlink. It's actually a link to proc self fd1. And this, again, looks like a file on a disk. It's got a path, right? But really, it doesn't exist on any file system. It's not on my hard drive. It's just a file that my process has opened. And my process is represented by proc self. You can look in here, and these are all, they look like files. Again, they're not on disk. They're just interfaces provided by the kernel, by various kernel drivers, to interact with my current process, which is this, terminal process. So I can look at like the command line that was used to launch it, for example, proc self command line, and since I'm creating a new process by calling cat, it's actually printing the command line of the new process, because proc self refers to my current process. If I want to, so whenever I type a new command here, I'm actually spawning a new process, and that's why I see cat proc self command in proc self command line, because that is the process. So if I look right now, my current process here, which is, I guess, sudo, I can also do like cat proc, I think 5617 command line. And I can see that this was started with sudo bash. And again, I can go look at fd. This is a directory, and I can see all the file descriptors that are open. So what's a file descriptor? File descriptor is an identifier for scoped to the current process. It's just an ID. It's just a way to refer to an open file. You could pass around like a big data structure that describes a file if you want to do a read or write, but really it's easier to just refer to it by its ID. Now the ID, it's like, an ID in a database table, for example. It's an identifier. It just is some way to pass around a reference to some data structure. So on the, if you're passing around a ID of a database row, you're really just passing around a pointer, in effect, not a memory pointer, but you're pointing around some reference to a data structure on disk that or not necessarily on disk, but represents that data. In the kernel on Unix, there is some data structure that represents a file that a process has open. That's some struct in C. We could go look at it in the kernel if we wanted to dig through the source. I don't know off the top of my head where it is, but shouldn't be hard to find. So this ID, somewhere internally in the kernel, there's something that says, okay, for my process, which is 5617, these are all the files that are open, 0, 1, 2, 3, 4, 5, 6, 7. So my process has 8 files open. And I don't know what these numbers really represent other than 0, 1, and 2. The kernel keeps track of that. The kernel knows, okay, file 7 for process 5617, is this file. And we can actually ask the kernel that. We can type list open files and then give it a process ID. And it'll show us everything that's open. Now you can see that this terminal uses a number of libraries. So we can see it's got some encryption stuff and some security stuff. And let's see, obviously the binary itself that we're running, sudo, we can see here is loaded. And then the file descriptors, so this 0, 1, 2, 3, 4, 5, 6, 7, that's these guys here. And we can actually see in this process what files are open. So we can see that 0, 1, and 2 are devpts3. Does anybody know what file descriptors 0, 1, and 2 are?
Standard in, standard out, and standard error.
Exactly, yes. So when you spawn a new process on Unix, we're talking about Unix here in general, so Linux, Mac OS, FreeBSD, whatever, Solaris. All these semantics I'm talking about, all this stuff is Unix specific. It doesn't really apply to Windows, but pretty much every other operating system. This is the model, and it works very well. So we have the standard input, standard output, standard error, devpts3. Again, let's just do a little experiment. So if I echo hello, and I just append this to devpts3, look, it shows up here. That's pretty cool. I can just treat this file, even though this file represents a terminal, I can still, echo to it, just like I would any other file on disk, but it's not really a file on disk. However, if I want to write to a file on disk, I can do echo hello, a file, cat a file, and it works the same. I can use the same API. Now this under the hood is really doing an open, this little like append shell thing. This is just, a shortcut of saying open a file for writing, write, this many bytes, and close. I can do that for a file, whether it's a terminal, whether it's a file on disk, whether it's my RAM, whether it's my video card or my sound card, or anything. Also a network socket, which is what I'm getting to here. Sockets really are just another kind of file on Unix, and the whole point, the advantage of making everything a file and using this same API to describe like a socket or a file on disk or my terminal is that I can use the same API. I don't have to memorize like this is the command to open a terminal, or this is the command to open standard input, or this is the command to open a socket. They're all there are extra functions you can use to interact with these various kind of subclasses of file, but open, read, write, close, they all work the same. Like there's no close socket system call. There's an extra system call called shutdown, which lets you say like, hey, I want to gracefully close down this socket and let the other side know about it. But really, you can just call close on a socket as well. If we didn't have this orthogonal API, this API where everything works the same more or less, like that's kind of a standard interface, then I would have one function for closing a terminal file, one function for closing a socket, one function for closing like a file on disk, and that's hard to remember basically. Why duplicate these things when we could just use the same semantics? So that's kind of the genius idea that's behind making everything a file in Unix, and it works very well. So let's look at actually making some sockets now. So pretty much all of these things like open, read, write, close, so on, these are system calls. These are services provided by the kernel that we as application developers can ask the kernel to do for us. And so all these system calls are documented. On Linux, you could just type man, open, for example. And this is showing us the open system call. So the open system call opens the path specified by path name. So you've all used this in some form or another. This is what it looks like in C, but if you do it in, say, Python, it's not really any different. In Python, you say open, you give it a string that represents the file you want to open, and then some flags, which will be like read, write, So it's the same in C, it's the same, the language doesn't matter. It's the same in Bash, whatever. Really, all of these languages just compile down to this system call. And we can go into that in more depth in another talk. Maybe system calls are pretty fun to talk about and read about. But the point is, we can use open, we can use read, write, close, and various other system calls on any kind of file. So we can see these are some of the other system calls that are related to files. So there's like link, stat, socket, write, mount, memory map, seek, so if you want to change the position in the file, make a FIFO, change owner, all this stuff. We know what these things are, some of them anyway. So let's look at sockets. So what's special about sockets? It's really just an endpoint. And the idea of a socket is it's two-way. You can read and write from a file, so it's not really, that's kind of two-way in a sense. But you can specify different address families that you want to use with the socket. Now, notice that it says it returns a file descriptor. Now, file descriptor is that integer ID we were talking about. So when you open a socket, you get a new file ID, basically. File descriptor returned by a successful call will be the lowest number file descriptor not currently open for the process. So we even know, if we have 8 files open and we ask for a new file descriptor, we'll get the 9th one, which will be, file descriptor 8, because they start at 0, of course, but it's quite explicit exactly what the file descriptor number will look like. So when we open a socket, we have to tell it what address family we want to use. And these are some of the families that are available. The ones you guys are probably thinking about when you're thinking about sockets in the form of networking are probably thinking about this guy, AF-INET. And so this is what's pretty standard today. We can also use UNIX. So UNIX is when you create a socket with a path. And so we saw that before. Let me get a sudo shell here. So we can do LSOF. Let's see, PS, LSOF, process, let's look at 6524. Actually, no, this doesn't have any Unix sockets open. Maybe we can look at some other process. So I have, Brave here. I can just grab, anything like Slack. Let's look at Slack. What does Slack have open? We can do LSOF, process, Slack here, and we can see we have 100 something file descriptors open. So we can see we've got like local storage, we've got some log file. These are actual files on disk, obviously, but there's probably some sockets as well. This let's see. So a Unix address family Unix socket is one that refers to a file on disk. You can use a file and treat it like a socket, like as if you were speaking to somebody over TCP, but just on the local file system. It's used pretty commonly. So like Postgres, for example, if you want to connect to Postgres, there's usually in var run, I think, there's a bunch of sockets in here, and usually there'll be like a Postgres socket. I don't know. I have it on here. Yeah, var run Postgres. Yeah, I don't know. There's things get stashed in here, or in like temp. And if you want to talk to a program on the local machine, you don't have to do it over UDP or TCP. You can actually just talk to it over a socket. I don't know where my sockets live right now, but it's not important. They're just on disk, they're given a path. And that kind of communication with sockets we call a UNIX domain. And those use the address family UNIX. But other than that, the only ones really used these days out of here are INET, which is IPv4, which is the one we're all most familiar with. And sometimes IPv6, which is a newer version, which is mostly the same, just has longer addresses. It's also Bluetooth here and some other things, but pretty much most of these are from like the 1980s, 90s. Nobody's using IPX anymore. This is very old, or most of these died out. AppleTalk is extremely old. I don't think it's been used in a long time. DECnet is from, I think, the 70s. I don't know. These are very old because until not that long ago, it wasn't a given. It wasn't known that like, oh, internet protocol is what we're going with. That's what everyone's going to end up using. That was not obvious at the time. And there may be new protocols in the future that we use, but IP seems pretty standard. So if we want to do some communication over the internet, we're going to want a socket with address family internet. So when you create a socket, you're going to tell it what domain you want to use, and that's going to be AF INET. So let's take a look at some code. Everyone's somewhat comfortable with C, maybe. So what we're going to do here is I have grabbed the source code for an example client and server UDP application. So let's take a look at what that is actually doing. So here is a server, UDP server. Now there's a number of different kinds of protocols that go over IP. So when we're sending a packet over the internet, at the lowest level, we're sending it over Ethernet or wireless Ethernet. And then we have an IP address with a destination, IP address source and destination. And then on top of that, we can put other protocols. So if I'm sending you a packet over the internet, I can send it as TCP, UDP, ping, which is IGMP, and ARP, which is for looking up IP addresses on the local network, address resolution protocol. But generally, the ones people use over the internet are TCP and UDP. The difference is that TCP has more overhead. So with TCP, you establish a connection before you start sending data. So you know that the other side is actually listening to you, and you have said like, okay, we're going to talk to each other. We've worked that all out. And when you send packets, you know if they get received or not, because the other side will acknowledge the receipt of that packet. And it'll do some, if it doesn't, if the other side doesn't say, hey, I got that packet you sent, it'll retransmit it a few times. So TCP is very good for reliable delivery of packets. If you want to make sure that your packets actually reach the destination and are in order, and that you are actually talking to somebody and they're listening, TCP is great. If you want to just send a high volume of packets, or you want to do it in real time, like if you're playing a game or if you're speaking over Zoom, for example, then you would use UDP. UDP doesn't have any of the overhead of TCP. You don't establish a connection. You don't wait to see if your message has been received. You don't retransmit. It's just you open a socket, you send data. You don't know whether it's received. You don't know anything else. You just receive or send data. So let's start with UDP because it's simpler. So this is what a UDP server looks like. So first thing we do is we do the socket system call. And socket takes a domain. So we give it AF INET. I think there's a typo there. That should be AF. I don't know what PFINet is, but normally it's AFINet. And then sock dgram. So here, the second parameter, typically there's sock stream, which is TCP, and sock datagram, which is UDP. So here we're saying, I want to use internet protocol, and on top of that, I want to use UDP. And then we have to create a structure that represents the address we want to bind to, the address we want to listen on. And so that consists of 3 parts. We say we create a struct, so it's called sockAddrIn. And this is a socket address for internet, IP, internet protocol. So we give it a family, and that's INET. We're using IP, and then we give it a address, source address, and we say ini, and ini is known as 0000. You've seen that before, and it's defined here as 000000. We can also do things like in address local, for example, or loopback, sorry. And can anyone guess what that's defined as here? Anyone know what this is? This is 127.0.0.1. So each of these is a series. This is an IPv4 address. It's got 4 octets, 4 bytes. First one is 127.0.0.1. You all know what that is. So the address here that you say to listen on, you can listen on all addresses, which is 0000, or you can listen on loopback, which is only connections from my local machine will be accepted, or you can listen on a specific IP address bound to, like a specific interface. So maybe you have a few Ethernet cards in your machine, or you want to listen on your local wired interface, but not your wireless one, for example. You could specify that here, which address you want to actually accept connections on, and that is usually mapped to a specific device. And then lastly, you specify the port number that you want. So here we're going to listen on port 5001. And then once we've set up this structure, the struct to contain the address we want to listen on, we call bind. Bind is another system call, and it takes a socket file descriptor as the first argument, and then it takes the address that you want to bind to. So we're just saying here, for my socket that I open, my UDP socket, I want to bind it to loopback to 127.0.0.1 on port 5001. That's all that this is saying. And then we call another system call, which is listen. And this says, okay, I want to start listening for incoming things on this socket. Like, I'm ready, let me handle input from the network, basically.
Yeah, okay, but this is for listening on the local machine, right? Yeah,
correct. So if I try to connect to this, connect is the wrong word because we're using UDP here. But if I tried to send data to this from another machine, I would not get it in this program because I'm not listening on all addresses. I'm only listening on this loopback interface, which is local only to my machine. It's a loopback device is one network interface. We can of course see them if we type ifconfig or IP adder. This is my loopback interface. We can see it is assigned 127.0.0.1. I also have an Ethernet interface, which is not assigned anything. I also have a wireless interface, which has this IP address. And then there's some other virtual interfaces as well for, I don't know, Docker or something. So these are the physical, or well, quote, physical interfaces with network. This one is automatic on any UNIX machine. It always exists. If you delete it, I don't know, something bad will happen. But the other, Ethernet and tunnels and bridges, those are, kind of fancy other goodies we can use if we want to talk to other machines. So again, right now we're doing this just on the local machine. It doesn't really matter what address we're using as long as we can talk to ourselves. So now here we're listening on the socket. We told our operating system, give us a file descriptor, bind it to this address, listen for datagrams. A datagram is just a packet. It's just like, hey, here's some data. Again, it's UDP. We're not asking to know if the other side got it. We transmit. It's just, hey, here's a packet. Maybe you get it, maybe you don't. Datagrams get lost. Nobody knows what happens to them. Doesn't matter. It's expected. So the last call that we're using here is receive. Receive is basically the same as read. So again, we can actually go and look up all these things. We should. We can type like man bind, for example, and it'll show us exactly how bind works. So when a socket is created, it has no address. So bind assigns the address, and then we can look up, listen, and see, marks the socket referred to by sockfd as a passive socket, one that'll accept incoming requests. I'm actually not sure if this is needed for UDP. This might only be for TCP. And the second parameter here is like backlog. So let's get into that later. It's not super important. So there's receive, and receive is just a special form of read. So we can see receive a message from a socket. Now, I did say that we can use the same file API with any sort of file. So like read and write, and that's true. We can call read. We don't have to use receive. So here I could just replace receive with read, for example, and it would work. It just doesn't have this last flags argument. So the flags argument lets you specify like if you want to block or not. So like there's, these are some flags you can pass that are special for sockets. But again, you don't have to use this. This is just if you want to use some special cool things you can do with sockets, but you can just use read as well. Both will work just the same if flags is 0, which it is right now. So we say receive, and receive returns the number of bytes that it read from the socket. And it'll block. And it'll read up to this argument. So I created a buffer. It's just a static character buffer, 512 bytes. And so I say read whatever is sent to me into this buffer on this socket. Whatever is sent to me on this socket, read into this buffer up to this many bytes. I got a -1 because I want to toss a null terminator on the end of it so I can print it like a string. But basically, when this finishes, if it's successful, bytes read will be some positive number, and buff will contain whatever I read off the socket. If it fails, if something goes wrong, it'll return a negative number, which will be an error code. And then I just print out here what I read after tacking a null terminator on it. So you can go ahead and run that, why not? So here I am running server, playing server. Okay, so the server is running, it's listening for connections, cool. Now we can look at the connections. We can look at the sockets as usual. We can do our LSOF. So let's find our application. Where's web server? Should see it here. So here's our server that's running. I can say lsof-p blah, and here's all the files that our program has open. It has libc as expected, ld, which is dynamic linker, standard input, standard output, standard error, and look, there's our UDP socket. So we can see here, this is the process, this is the user, this is the file descriptor, see fd, so file descriptor 3, because it's the lowest number after 2. It's IPv4, so this is AF-INET. This device, I don't know what that means. That's some internal kernel thing. I don't know what this is. And then we can see this is listening on port 5001 UDP. Pretty cool. I don't know why Pulse Audio is in here. That's kind of strange, but whatever. So we can see that our server is listening. We can inspect it here. We can also, there's lots of other ways to look at open files and sockets. There's a cool tool called SS on Linux. Just another utility to investigate sockets. Pretty straightforward. So we can pass -L to see what's listening. We can pass, I think, -U to see UDP. We can say print the process. We can say, so it'll try to fill in some names. Sometimes these are right, sometimes these are wrong. This is just a mapping of port to name, to service name. You can find those in, it's services. So you can see here, like SSH 22 TCP. Cool. So that's where these names here are coming from for port. We can also say in to say don't translate for us. We don't care, because sometimes these are wrong. You know, these are just a mapping, but you know, just because some port has been defined as being some specific thing, it's not always used for that specific thing. And a lot of things like, I don't know, Zoom will start stuff up on its own ports, which aren't defined anywhere. So we can see what process, you know, is listening on this port. Server should be in here. There it is. And we can see process ID 6957, file descriptor 3. Again, these are numbers that mean something to the kernel, but don't really mean anything to us. I mean, we, you know, they're just references to some internal data structures. So there's a task data structure that kernel has somewhere, an array, and this process struct is index 6957 in that array. Same with the file descriptors. And yeah, so we can see here what's listening. We can see all the processes that are listening on our machine. It's sometimes interesting to take a look at that, see what kind of shit you have running. And we can also watch what's being sent over that port. So let's get to that in a second. We can also, another great tool, by the way, while we're here, we can dig into this more another day, but is strace, which lets us show the system calls that are being made by a particular process, which is pretty cool as well, 6957. And we can see right now, if we attach, it's calling receive from, which is what we're doing here. We're calling receive. Receive just expands to receive from with a bunch of default arguments. But we can see it's calling receive from on file descriptor 3. That's exactly what I wrote here, receive from sockfd. Pretty cool. Great tool for debugging. So let's go ahead and send some data to our server. So I have a client here. Let's take a look at that real quick. There's not much new in here. We do the same thing. We say, give us a socket, inet, dgram. We say port number 5000. We aren't really specifying a server address. Oh, this is source address, sorry. And then we basically just call send to. So there's receive from, send to. We just say, we're gonna send this string, hello from client. Give it the length of the string, of course, some flags, and then the destination. This might or might not work. Let's take a look. And it just does it in a loop here. Great. So we can see here, every 3 seconds, we're sending hello from client. Send to also returns the number of bytes sent or negative if an error. Again, it's just the counterpart of receive from. So we can see here, we're reading 17 bytes and then printing it out. Everything's working nicely. We can go here and look at strace, and we can see we're calling write. We call receive from. Okay, let me stop this so we can see. So we call receive from 3. So we're saying, okay, give us, and then when it completes, it actually prints out the rest of the call. This is pretty cool, actually. We see it fills in the rest of the parameters. So this was, sockfd, buff, size of, and that's what we have here, buff, size of, 512 minus 1 is 511. So we can see exactly what this program is doing. Even though it's compiled, we don't have, here we don't have any access to the source code or anything. We're just looking at it, but we can see exactly what the program's doing. That's cool. I love this tool. And then we call write, read 17, and that's this line here. See, we call printf read bytes read. Now we see it's calling write 1. What does that mean? Y'all know we're printing the standard output. And we're saying print to file descriptor 1, this buffer, and it's 8 bytes. And we do it again to print what we received. We call receive from again. Just what we have here. Nothing crazy. Now, if we want to look at what's being sent, we can do that too. So let's go ahead. I guess it's still running. Cool. Let's look at, okay, so we can do TCP dump. This is a pretty cool tool. It's not just TCP, it's other protocols as well. We're going to say, I want to look at what's going on the loopback interface, 127.0.0.1. And I want to print it out ASCII and hexadecimal. And I want to look at UDP port 5001. Boom, there it is. So we can see this is what the UDP packets look like. It's got some header stuff, but it's a simple packet. It's sent from localhost to localhost on port 5001, UDP, 17 bytes. And there's the 17 bytes. All this stuff above it is some protocol headers. So this is, I think, mostly IP packet. If we do this over Ethernet, we would see some Ethernet headers as well. But it's a simple packet, basically. This number here is the source port. This is this is more just used to keep track of the socket on the client side. The client side source port has nothing to do with the destination port. The destination port is the port we're listening on. The source port, that's basically a random number. Again, just used by the kernel to keep track of this connection, or not even connection, but that's what we're seeing here in TCP dump. Again, excellent tools you can use for debugging lots of kinds of applications and even problems with web applications. I've definitely used these things for debugging web app problems before. So that's TCP. I think, sorry, that's UDP. That's what it looks like, single packet. No response, no connection setup, no nothing. Just here's a packet. Here's a datagram. Okay.
You said that we can also, just so as that we can use TCP dump to listen to both TCP, UDP, and ping, right?
Correct. Yeah, you can use TCP for lots of things besides TCP.
Okay. Cool.
Certainly. If you've ever used Wireshark, that's the same thing as TCP dump. It's just not named. Yeah, it's named wrong. That's, well, whatever. Okay, let's look at TCP and let's dip out of C. I wanted to use C to kind of show you exactly. It's very close to the system calls that are actually being made, which we can see with strace, and it's, shows that doing network programming, there's a few steps, but it's not too bad, even in something as low level as C. And this code, this will work on any Unix system. It'll work on FreeBSD, it'll work on Linux, it'll work on a Mac. It's all very standard. It's defined in the POSIX standard, which is another story. So I didn't even make, I just grabbed these examples, but I copied over a client and server in Python, which is going to look similar, but with a lot less kind of junk. So here we're going to do the same thing, except we're going to use Python. We're importing socket here. And we're going to say socket.socket. Again, this is just the same TCP socket system call we're familiar with. Or sorry, not same socket system call. This Python module, as you can see, exports all the socket related system calls that you might want to use. And then we're going to use AFINet, and then we're going to use socket stream. So this is not, the other one was socket dgram, as you may recall. This is UDP. Socket stream is TCP. Again, we call bind on the socket. So here we can see it's more of like a object-oriented style in Python. It's kind of cool. And we give it an address to bind on. And the address is really a tuple of address and port. So again, here we're binding to localhost. We can bind to all addresses if we wanted. I could even bind to, for example, I could bind to my wireless IP, and then only things in my wireless network could connect, for example. Port 5001, and then bind, and then call listen, and then we listen for connections. So this is a little bit different from UDP. I'm not sure if we need listen for UDP, but what's different is we have this accept here. With TCP, you have to establish a connection before any data can be sent. And to establish a connection, you call listen, and then you call accept. And then accept will block. This will block and wait for someone to connect. And then we can print out who connected, and then we sit in a loop, and again, we call receive. And again, this is the same receive from call we were making in C. It's the same system call, it's just kind of written out a little bit nicer. But we're just calling receive on a file descriptor, sock accept. We can, of course, go here and type man accept and read the man page. This is not it. Man 2, yeah. Again, just because we're using Python, it doesn't matter. It's under, Python is just calling this same system call. So it extracts the first connection request on the queue of pending connection for the listening socket, creates a new connected socket, and returns a new file descriptor referring to that socket. So that new file descriptor is going to be connection here. It's buried in this socket object that Python abstracts, but it's just a file descriptor. So again, we can call receive on that file descriptor, and then print out what we got. And then here we call send, just to send back. It's an echo server. And then at the end, when we're all done, if we got some errors or whatever, then we call close on the connection. And we do this in a loop. So every time we get a new connection, we do this stuff, and then when it's done, we close it and go back to waiting to accept a new connection. Python server.py. And so here we're waiting for a connection. We can, of course, go see ss-l and t, see TCP. So here we can see all of the sockets listening for connections that are TCP on my machine. And we can throw in a P to see the process. So, I got Postgres, I got some other stuff, and here's our Python application. Again, file descriptor 3. Here's our process ID, port 5001. We can see it's listening on any address. And then we can connect. Let's take a look at our client here, client.py. Pretty basic stuff. So here's our address. It's the host and port. We call socket connect. And then we just connect and we say, this is the message. It'll come back to us. And then we call sock receive to see what the server sends back. Again, it's an echo server, so we should send something and receive something. So let's go ahead and run the client, client.py. Sorry, Python 3, client.py. And there it is. So we can see here, we're waiting for a connection. We got a connection. We can see this is the client. So this is the client's address and port, source port. Again, don't really, port's just some random number, the source port. We got this data, and then it disconnected. So, and now it's listening for a connection again. So I can do this as many times as I want. And each time it's doing a new accept. So if we want to look at the TCP dump, we'll see something a little bit different this time. So I can dash interface loopback, canonical output, TCP port 5001. Okay, now if we run the client, what do we see? Whoa, look at all that. So here's the message we sent, here's the response. But there's a lot of other stuff, and this other stuff here is the TCP overhead. So you can see it's there's quite a bit more stuff going back and forth compared to UDP. So the first thing that's sent is a SYN packet, SYN, for synchronize. And it says, okay, we're sending from localhost on our source port to localhost 5001. This is the first packet the client sends, and it's sending a SYN packet, S. And then the SYN packet says, I want to open a TCP connection. And it has some other data in here, but that's basically what it says. The server then here responds to the client with SYN flag ACK. ACK stands for acknowledgement. So here we send sequence blah, 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 62, and then we acknowledge sequence 63. We increment the sequence number by 1, I think. So this packet says, yes, I'm acknowledging your synchronization packet that you sent me. I want to establish a connection. And then the client says, I acknowledge that. Let's begin. And then the client sends out the server. And then once the client has acknowledged the acknowledgement, the client sends to the server payload. So That's the payload here. We can see it's got P. We can see that this packet, this payload packet, is bigger than the UDP equivalent. I'm not going to find that, but trust me, this is a bit longer, and it's because it has some extra TCP headers about sequence and some other stuff that we're not going to get into. So it sends this packet to the server. The server says, acknowledge that packet. So see, this is sequence 143, and we say acknowledge 43. We say, yeah, we got that. So if the server didn't send this acknowledgement, the client would retransmit this until it's received. So this is kind of the reliable part of TCP. It's everything that you send, the other side says like, yeah, I got that packet. So you know, stuff doesn't get lost, basically. Or if it does get lost, you know about it. And then the server sends to the client the same message. This is the message. This is the echo part of it. Client accepts that it got that message. So cease, send, acknowledge. And then here we are done. And so the client sends a finish flag, fin, that says, okay, I'm done. Thanks, bye. And then the server, of course, acknowledges it, and then the client acknowledges that, and then we're done. So that's what a TCP connection looks like. Any questions?
Can you run socket accept in multiple threads and serve multiple connections at the same time?
That is a great question. Yes, I wanted to talk about that. So sock accept here. So yeah, usually the flow is, if you're writing a real server like that, you want to accept random connections from the internet on, yes, you call accept, it gives you a new file descriptor, and then usually, yes, you would either start a new thread to do something with that connection, or you would fork here, and then that would, do essentially the same thing. It's just two different ways of doing the same thing. But yes, you want to start another thread of execution to process that connection, because right now, while I'm the way this is designed right now, this can only have one client at a time. This loop here, I'm not like accept isn't really being called. So while I'm handling this client, I can't accept any more clients. And so that would be the best practice. Yeah, you would start a new thread or a new process by forking, and you would process that client connection. You would do all this stuff in a separate thread and then go back to calling accept. Now there's a bit, even if you do that, even if here we were to fork and then continue on, there would be a little bit of a race condition. We would, in between accept and when this fork stuff is done and we come back to accept, we wouldn't be able to accept any new clients. There's going to be some delay between when I do whatever I'm doing here and then loop back around and call accept again. So in that time, there's kind of a buffer of waiting clients. So except when I call again, if there's other connections kind of buffered up, then I can just call accept will return immediately that new connection. How big that buffer is actually this parameter, this one. So right now I just have a value of 1, which means don't buffer. But if I set like 1,000, then even if 1,000 connections come in between like after I call accept here and when I call accept again, it'll be okay. It'll buffer that up. After 1,000, then I think the client will probably get some error. I don't know. But yeah, that's what this number is. It's called the backlog. We do like man listen. You can see int backlog, and refers to the maximum length of the queue of pending connections for socket FD may grow. If a connection request arrives when the queue is full, the client may receive the connection refused, or it may retransmit later. Yeah, good question. That's all I was planning to talk about, just basics of sockets. If you're curious what a WebSocket is, it's kind of this overall, architecture, like structure, but it's much more high level. It's a web API. It's a standard, I think, W3C standard probably, and it lets you just do kind of real-time read and like send and receive of packets, but from a web browser. It's under the hood somewhere, probably using this kind of Unix sockets, but it's much more high-level kind of protocol. Okay, any questions? Anything else you guys want to know about?
So can we basically think about our backend as glorified sockets?
Absolutely, yes. Well, yes. So when you run your Flask dev server, for example, that is a socket. When Amazon is running lots of sockets on, say, API Gateway, for example, which is usually what's listening on the outside world. Let's see, maybe I can start this up. Let's see, I don't know if don't I have a virtual environment? What's wrong? Oh, I guess there's something wrong with my virtual environment. But yeah, if you were to start up your Flask dev server, for example, you can go look at the sockets on Mac OS or on Linux and you'll see the exact same thing. You'll see something, it'll be just another one of these processes listening on the socket. Yeah, totally.
And it's usually TCP.
Yeah, so for most web stuff, TCP is commonly used, although new stuff is a bit more complex because, well, that's a whole nother story. Quick, there's a thing called Quick you can look up if you're curious that more web stuff is using now. And this is designed for rapidly opening connections, web connections, without the TCP connection setup overhead, I think. You can read all about this if you want, it's cool, but I don't remember exactly how it works. But in general, yeah, it's TCP because you don't want to lose parts of like whatever you're downloading. Like if you lost a packet of your JavaScript, then your JavaScript wouldn't compile. So we want some reliability. Okay, I hope that was informative.
Yeah, cool stuff. Thank you.